Hello everyone. Today we will discuss chapter 2 of Thermodynamics 2, Vapor Power System, or it is chapter 8 in the textbooks. We have learned the basic principle of this power system in Thermo 1. In the Thermo 2, we will study it in more detail, especially on how can we improve the performance of this power system. This is the learning outcomes of chapter 2. First is to explain the basic principles of vapor power plants. Secondly is to describe the effects of varying key parameters on Rankine cycle performance. And the last one is to discuss the principal sources of Exergy destruction and loss in vapor power plant. This is the content of this chapter. First, we will have a quick review of the basic principle of vapor power plants. So it is pretty much similar to what we learned in Thermo 1, just to refresh our memory. Second one is improving the system performance. So we will see how is the system modified to improve the performance. So in this case, we will see the addition of superheater, reheater, and also a supercritical system. So this is an ongoing research, supercritical vapor system. And second one is regenerative vapor power cycle. And then we will have a look on the working fluid, cogeneration, and carbon storage. And the last one is looking at the Exergy accounting for this power plant. The first topic is review the basic principles of vapor power plants. So in Thermo 1, I think I show you this schematic. So this is a simple schematic of a vapor power system consisting of four block system. The block on the left side, it is block system A. This is the combustion system. So we have a boiler along with the combustor. So in this case, the energy source is a fossil fuel, this one. So we have a fossil fuel and air entering the combustor, and there is a combustion there, and then there will be a conversion from chemical energy into thermal energy. And this thermal energy will boil the water and generate a steam, and then it will flow to the turbine here. And then going to the right, there is another system. It is system B. So this is the Rankine cycle, or the vapor power cycle part that we will learn. So it has four important component or principal component there. One is boiler, and the second one is turbine. So turbine generate a power. So the turbine converts thermal energy. So this energy is coming from the working fluid flowing through the turbine, and then this power is transferred to the electric generator to generate electricity. And then the working fluid will flow to the condenser. So in this condenser, the thermal energy is damped out of the system. And in this example, we use cooling water, and it's flow through the condenser and then take the thermal energy and then flow out of the condenser and going to the cooling tower. Okay, and then exiting the condenser, the working fluid phase is usually either saturated liquid or compressed liquid, and it will be pumped to the high pressure, similar or slightly higher than the boiler pressure, and the working fluid will going into the next cycle. So once again, in the system B, which is the heart of the power plant consists of four principal components: boiler to generate steam, and then turbine to generate the power. So there's a conversion of energy inside the turbine here from the thermal energy to the power, so mechanical power. And then the next one is condenser, where the thermal energy is sent out of the system going into the environment. And the last one here is a pump, so to rotate the working fluid back to the boiler. And then system C here is the electric generator. So the generator will convert the mechanical power here into the electric energy, and then it will be transmitted to the electric network and then going to our community. And then the last system, it is on the most right side here, is the cooling tower. So this cooling tower acts as the part that will damp out the energy from this warm water into the environment. So in this case, it's cooling tower, and in other case, it might be just ocean. So there will be a pipe underneath the ocean that will transfer the energy from the warm water into the ocean. The next one, it is pretty much the same except the combustor system. So in the previous slide, we use fossil fuel combustion to provide the chemical energy that converted into the thermal energy. So in this figure, we have a pressurized water reactor. So this is a reactor. So if you see this figure, so we have a reactor vessel, and then we have a pump here to recirculate the working fluid inside this pressurized water reactor. Then there will be an energy transfer here from high temperature working fluid inside the reactor into the working fluid of the vapor system. So there will be a steam generation, so represented by a small sphere here. It might be like kind of bubble here. So inside the boiler, we will have a steam with high temperature, and then entering the turbine, and the turbine will convert this thermal energy into the mechanical power, and so on and so on. And then this one is using solar energy to provide the energy for the vapor power plant. So this one is the receiver of the solar energy, and then it will be collected and transferred to this working fluid. They say here is molten salt or oil here that will grab the solar energy, and then it will flow through this small piping and going into this heat exchanger, which is a kind of boiler as well. And then the system on the right side are the same as the previous slide. So we have a turbine, condenser, pump, and then electric generator, and this one is the cooling tower. And then the last one here is the vapor power plant that use geothermal energy. So assuming here we take the hot water from underground, and then it is pumped through this pipe and then flows through the heat exchanger, which is the boiler, and there will be a transfer of energy from this hot water and steam into the working fluid of the vapor plant, and then this hot water will enter the turbine. Turbine will convert this thermal energy into the power, and so on. So there are several options for the source of this vapor power plant. So it can be from the fossil fuel. So this is the most popular one. So even in the United States, they still have coal as the fossil fuel, and this is the largest portion of the energy source for the vapor power plant. So there is also nuclear reactor as the source of the energy, but I think the percentage is still lower than the one from the coal. So to model this Rankine cycle, we can looking at individual component of the system. First, we can look at the turbine system here. So we apply an energy balance. So the turbine is treated as an open system or control volume system. So the volume is constant and the mass is allowed to flow across the boundary. So in the turbine, usually the process is assumed adiabatic. So in this case, Q is 0. And then WT here is the power generated by the turbine. And then the flow energy following the mass flow is represented by this term. So the flow energy in is actually the enthalpy plus the kinetic energy plus the potential energy, and the energy flowing out of the turbine is same thing. So it's enthalpy plus the kinetic energy plus the potential energy. So assuming that the contribution of the kinetic and potential energies are neglected, so we have equation 8.1 here to estimate the power generated by the turbine. So this is just the difference of the enthalpy between in and out. And then similarly for the condenser, we can apply the energy balance and we will get equation 8.2. So the heat transfer sent out from the condenser, here is the enthalpy difference between in and out. And then for the pumping, so the power required by the pump, which is actually taken from the turbine power, is the enthalpy difference between exit and inlet. And this is for the energy required to generate steam inside the boiler. So if you look at this formula, so all number here are positive. So when we analyze a power system, we try to keep all number positive to avoid confusion. So in this case, we don't follow the convention in the previous chapter. So in THERMO 1 or with this chapter 2 or 3. So if you remember, the work is positive when the system is doing the work, and the heat transfer is positive when the system is receiving the heat transfer. So once again, to avoid confusion in the analysis of Rankine cycle or vapor power system, usually we maintain all numbers positive. And for the performance of Rankine cycle, so we have efficiency here. This is the ratio between what we gain. So what we gain here is the turbine power minus pumping power. Okay, so and then divided by what we pay. So in this case, the energy required to generate a steam, Q in. So energy going into the boiler here. So equation 8.5a here is the efficiency of the Rankine cycle. And then you can manipulate this equation so that you can get equation 8.5b. So you can see that the efficiency is 1 minus the ratio between H2 minus H3 over H1 minus H4. And then another parameter that is used to quantify the performance of Rankine cycle is heat rate. So this represents the required heat per unit power. Okay, required heat per unit power. So this is Q in over power. So I think this is net power. So this is turbine power minus pump power. The performance number 3 is what is called back work ratio, BWR. So this is the ratio of the pump power over turbine power, equation 8.6. So I think we have learned each of these parameters in THERMO 1. So this is just a quick review to refresh our memory before we go into the next section, which is about system modification and how can we improve this Rankine cycle performance. Okay, this is an ideal Rankine cycle description. So on the right side, we have a TS diagram of this ideal cycle. So process 1 to 2, this is isentropic expansion of the working fluid through the turbine from saturated vapor. So you see here, state 1 is right at the dome line on the right side. So it means it is saturated vapor. So isentropic expansion of the working fluid through the turbine from saturated vapor at state 1 to the condenser pressure. So state 2 here. So this is a higher pressure, which is the pressure at the turbine inlet. So I can say this P1, and this is P2. So this is condenser pressure. And then process 2 to 3, this is a process of the heat transfer from the working fluid as it flows at constant pressure through the condenser exiting a saturated liquid at state 3. Okay, so from 2 to 3 here, there is a heat transfer from the working fluid into the environment. Okay, and then at the exit of the condenser, the working fluid phase is saturated liquid. So you can see that the point number 3 is at the dome line. It is on the left side, saturated liquid. And then process 3 to 4, this is isentropic compression. So keep in mind isentropic, so it means adiabatic, internal reversible. Isentropic means there is no change of the entropy. So if you see there, the line connecting 3 and 4, it is a straight vertical line. So it means S3 equal to S4. That's why it's called isentropic compression. Also similarly between point 1 and point 2, this is isentropic expansion, S1 equal to S2. So back again to process 3 to 4, isentropic compression here is inside the pump. So the working fluid is compressed to the liquid region number 4. So point number 4 here is on the left side of the dome, so it means it is compressed liquid. And then process 4 to 1, so this is heat transfer to the working fluid. So this process occurs inside the boiler. Okay, heat transfer to the working fluid as it flows at constant pressure. Okay, so P4 equal to PA equal to P1. Okay, so the line connecting point 4, 1, point 4A, 1 here is at certain pressure. This is P1. So process 4 to 1 here is a heat transfer to the working fluid as it flows at constant pressure through the boiler. And this will complete the process because the working fluid is back to the state of point 1 again. So it's doing a cycle here. So looking at this TS diagram, the area under the line connecting point 4, A and 1 here represent the heat transfer to the working fluid. Okay. Then the area under the line connecting point 2 to 3 here represent the heat rejected from the condenser. And the difference, so between these two heat transfer is the net power. Okay. So here, so this is the power. Okay. Okay, next one. For internal reversible process, and in this case for the process occurs inside the palm, so we can use correlation 8.7a here to estimate the power required by the palm. So this is the integral from point 3, which is the palm inlet, to point 4, palm exit, phi dp, okay, phi dp, and phi here is evaluated at point 3. Okay, dp is the pressure difference between point 4 and point 3. So you can see here equation 8.7b. So you can use this equation to estimate the pumping work. Okay, we also look at the effect of boiler and condenser pressure in THERMO 1 to see how do these parameters impact the Rankine cycle performance. So on the left side here, we increase the boiler pressure from P1 to P1 prime, or P1 with apostrophe here. So from the Carnot efficiency formula, by increasing this boiler pressure, the efficiency will increase. So if you remember the Carnot cycle efficiency, it is equal to 1 minus T in the cold side. So I can say here is the boiler, or Tc, the cold, over Th, which is hot. Okay, so when we increase the boiler pressure, so it's mean Th sorry, Th increases here from the average between 0.4 and between 0.4 and 0.1 here to the average between 0.4 prime and 1 prime. So Tc stay the same, so this is the same, and then Th increases, then the system efficiency increases as well. Similarly, on the right side, if we fix the boiler pressure while we decrease the condenser pressure, it means we lower a Tc. So using the same formula here, so lowering Tc while maintaining the same Th will increase the efficiency. Okay, so if we increase the boiler pressure, or if we reduce the condenser pressure, the system efficiency will increase. And then this feature is also showing the comparison between the Carnot cycle with the Rankine ideal cycle. So the Carnot cycle of this Rankine cycle is represented by the process line of 1, and then 2, and then 3 prime and 4 prime. Okay, while the ideal Rankine cycle is represented by point 1, and then 2, and then 3, 4, and 1. So if we compare this ideal Rankine cycle versus Carnot cycle, the ideal Rankine cycle has a benefit in terms of the temperature difference, or in this case the energy absorption from this combustion product into the working fluid. So if we use a Carnot cycle, so it's mean we can cool down this combustion product up to this temperature at 4 prime or 1 here. But if we use ideal Rankine cycle, we can cool down this combustion product up to 0.4 ideally, yeah, okay, ideally, but we will never reach this 0.4. Okay, so in this case we have a better combustion product energy utilization when we use ideal Rankine cycle compared to the Carnot cycle. Okay, in Thermo 1, we also introduce irreversibilities and losses inside individual component. The first one is if we have irreversibility within the turbine, then at the exit of the turbine, with this point 2 here, the entropy is higher than the entropy at point 1. So although the process is adiabatic, but we have internal irreversibility inside the turbine, so that the entropy increases. So in this case, we have additional parameter, which is turbine efficiency. This represents the actual power over the isentropic power of the turbine. So H1 minus H2 divided by H1 minus H2S. H2S here is the condition for isentropic process inside the turbine. Similarly, for the pump, we have a pump efficiency. This is the ratio between isentropic pumping work over actual pumping work. Okay? And we can use either equation 8.10a or 8.10b to estimate the pumping or the pump efficiency. Okay, we have completed this quick review of basic principle for a Rankine cycle. Now we are moving forward to the topic on how can we improve the vapor power system performance. So the representation of a vapor power cycle considered thus far do not depict actual vapor power plant faithfully. So if you get a chance to look at a nearby power plant, the actual power plant is much more complicated. So it has a lot of additional component, and the goal of this component complexity is to improve the system performance, which is efficiency. So various modifications are usually incorporated to improve overall performance. And we also saw an increase in the boiler pressure or decrease in the condition pressure increases the system efficiency, but it may result in reduction of the steam quality at the turbine exit. So you can easily looking at this two figure. So on the left side, if we increase the boiler pressure at the turbine exit, the state will be at the 2' here. And then if you don't increase the boiler pressure, the state at the turbine exit is at point 2. And clearly you see that the steam quality at point 2 is higher than the one at point 2'. So once again, although increased boiler pressure improve the efficiency, but it might impact the wear rate of the turbine because we have more two-phase flow inside the turbine that might erode the blade of the turbine. So similarly, if we decrease the condenser pressure here from point 2 to point 2', you see that the point 2', here is not prime, this one is a quotation, so double prime here. So the steam quality at this two quotation has a higher liquid portion compared to the one at point 2. Okay. And once again, it is not good for the wear, or it's not good for the lifetime of the turbine. Now let's have a look on the system modification that is widely used in actual vapor power plant. The first modification is by having a superheater. So in a basic Rankine cycle, the working fluid entering the turbine is at saturated vapor, which is 0.1 in this figure. Okay, and then further energy can be added by heat transfer to the steam and bring it to a superheated vapor condition at the turbine inlet. So instead of 0.1, the working fluid enters the turbine at 0.1 prime. So showing in this figure. So we can use a spirit heat exchanger to heat up this steam. So in addition to a boiler, we have additional heat exchanger that add more energy to the saturated vapor and bring it from 0.1 to 0.1 prime. And the combination of this boiler and a spirit heat exchanger is usually called steam generator. By looking at this TS diagram, we can see several advantages by having a superheater to the standard Rankine cycle. First is, by looking at this TS diagram, you can see now that the temperature at the hot side increases. So before we have a superheater, TH is the temperature average between 0.4 and 0.1. And then by having a superheater, the H now increases because the new average temperature is the one between 0.4, 0.1 and 0.1 prime. So once again, the Carnot efficiency of this Rankine cycle is 1 minus Tc over Th. So by having higher Th, then we will have higher system efficiency. The second benefit that we get by having a superheater is the increase of the capacity. So before we have a superheater, the net power produced by the Rankine cycle is the area surrounded by the process line 1, 2, 3, 4A back again to 1. So this is the area that represents the net power. And then by adding a superheater, now we have additional power from this system, which is represented by this area. Okay. So I don't see this benefit mentioned in the textbook, but you did see in this TS diagram that the area surrounded by the process line is larger. And then the benefit number 3 is the increased steam quality. So without superheater, the steam quality at the turbine exit is at this point, point 2A. Now by having a superheater, the steam quality increases, so it's going to the right, and it is now at point 2 prime. So by having a superheater, we have 3 benefits there: increase system efficiency, increase system capacity, and increase steam quality. And the last benefit here is good for the turbine lifetimes. The second system modification that is widely used in actual vapor power plant is by incorporating a reheater. So in this case, we have a turbine with more than one stage. So in this figure, you can see we have 2-stage turbine. The first one is high pressure turbines and the second one is low pressure turbines. So the steam expands through the first stage turbine, so high pressure turbine. So this is process 1 to process 2. And this expands to some pressure, and this pressure is between steam generator and condenser pressures. So at the exit of this first stage turbine, the steam is further reheated in the steam generator and then doing a process from point 2 to point 3. So here, let me show you. So we have point 1 here entering the first stage of the turbine and then exit the turbine at point 2. From this point 2, it is reheated to point 3. And then it goes to the second stage of the turbine, which is low pressure turbine. So both turbines produce work that will be coupled to the generator to produce electricity. And then at the exit of the second stage turbine, then the working fluid is flow through the condenser and then doing a similar process like the basic Rankine cycle. So by looking at the TS diagram on the right side, by having a reheater here, you can see that we can still maintain a high temperature in the high pressure side, this one, while maintaining high steam quality at the turbine exit. So imagine if I don't have a reheater at the turbine exit going to the condenser, the steam quality will be at 0.4 prime here. But now, if I have a reheater that reheat the steam from 0.2 to 0.3, I have a better steam quality at 0.4. So once again, by having a reheater, I can still maintain high system efficiency because of high pH while maintaining high steam quality at the turbine exit. For this analysis of the ideal reheat cycle, when computing the thermal efficiency of a reheat cycle, it is necessary to account for the appropriate turbine powers as well as the inputted heat. For the turbine power, so the total work developed by the two turbine stage must be incorporated or must be accounted for. So in here, we have the power from the high pressure turbine and the power from the low pressure turbine. So process 1 to 2 and process 3 to 4. Accordingly, so we also have a heat transfer added to this system, Q in. First is to the boiler, which is the process from 6 to 1, as well as the heat transfer or the added heat to the reheater, which is 0.2 and 0.3. And the efficiency of this ideal reheat cycle is formulated by this equation. So the efficiency is the ratio between the net power, which is the sum of the high pressure turbine power plus the low pressure turbine power minus the power required by the pump over the total added heat transfer to the system, total Q in. So this is the Q in to the boiler plus the Q in to the reheater. So Q61 plus Q23. The next system modification is by having a supercritical cycle. So the temperature of the steam entering the turbine is intended to be as high as possible. However, the level of this temperature is restricted by metallurgical limitation imposed by materials used to fabricate superheater, reheater, and the turbine itself. So high pressure in the steam generator also required a piping that can withstand great stresses at elevated temperature. So once again, our goal from the efficiency perspective is to have the temperature as high as possible, but it is limited by the material capability. Massive research now allows a vapor power plant to operate with steam generator pressure exceeding the critical pressure. So if you look at this dome peak feature, the critical pressure is at this dome peak. So we have a critical pressure here, and we also have a critical temperature there. So massive research on this material now allow us to operate a power plant to be higher than the critical pressure. So for water as the working fluid, the critical pressure is around 22.1 megapascal or 221 bar. It is equal to 3203.6 psi. So this plan that operate at this supercritical temperature or above a critical pressure is known as the supercritical vapor power plant. Look at the TS diagram on the right side. By having a supercritical cycle, the process from 6 to 1, so 6 here is at the pump exit to point number 1 here, doesn't intersect any area inside the dome. So this means that we don't have a clear phase change from point 6 to point 1. This also means that we don't need to use a boiler to change the process from state 6 to state 1. So we can just use a simple pipe here and then apply a heating to the pipe, and then the working fluid will change the condition from point 6 to point 1. So today's supercritical vapor power plant produces steam at a pressure and temperature near 300 bar or 30 megapascal and temperature of 600 degrees C. And if we have a system that operates at this condition, the thermal efficiency can be up to 47%, while the subcritical plant, the efficiency is only 40%. And then if we use a super alloy with improved high temperature limit and corrosion resistance, it enables a further high pressure. So in this case, we can operate or we can design a system that can work up to 35 megapascal or 350 bar. And at this operating pressure, the thermal efficiency of the system can exceed 50%. So you can see the benefit of having a supercritical cycle to have a high system efficiency. The supercritical research is still ongoing at Southwest Research. I know there are several groups that are doing research on this supercritical. So this is still a hot topic for improving the Rankine cycle. Let's take a look on this example. We have steam as the working fluid here for an ideal Rankine cycle, and this Rankine cycle is equipped with a superheater and a reheater. So steam enters the first stage turbine at 8 megapascal, so 80 bar, and temperature of 480 degrees C, and expand to 0.7 megapascal. It is then reheated to temperature of 440 degrees C here. Let me check my pen. Stop to operate here. Okay. Before entering the second stage turbine, where it expands to the condenser pressure of 0.008 megapascal. And then the net power output, okay, in this problem, the net power output is given. It is 100 megawatt. The first question is determine the thermal efficiency of the cycle, and then the mass flow rate of steams. In this case, because the net power is given, then we can calculate the mass flow rate of the steam. So the unit here is kilogram per hour. And then question number 3 is the rate of heat transfer, Q out, from the condensing steam as it passes through the condenser in megawatt. And also we need to discuss the effects of reheat on the vapor power cycle. So what this means by this question is we need to compare this Rankine cycle with reheater with the one without a reheater. I believe in the textbook it is example 8.1, and we show it to you in THERMO 1. But I think I look at that example 8.1, and it has a efficiency of 37.9, and we need to compare with this modified system whether the efficiency increases or not. Okay, let's take a look on the solution of this example. So the first step, what is known here is an ideal reheat cycle operates with steam as the working fluid, and then the operating pressures and temperatures are specified, and also the net power output is given. And then we have three questions. First is the thermal efficiency, and then the mass flow rate, and then the Q out. And then we need to compare it with the system without a reheater. And then the next one here is the schematic and the given data. On the left side is the schematic of the system. So entering the first stage turbine, it is point number 1 here. Temperature and pressure are given. So 880 degrees C and 8 megapascal. And then at the exit of the first stage turbine, the pressure is 0.7 megapascal. So this is point number 2 here. And then the working fluid is reheated inside the reheater, this one. And then it exits at 0.3 here, and the temperature at 0.3 is given. It is 440 degrees C. And then it goes through the second stage turbine, and then there will be a power generated by the turbine here. And then at the exit of the second stage turbine, here is the state number 4. And then from number 4 here, the working fluid flows through the condenser. There will be a heat transfer out of the condensing working fluid. So there will be a, let me make here, this will be the Q out. This is the question number 3. And then at the exit of the condenser, it is a saturated liquid here. And then the pressure is a 0.008 megapascal. And then from 0.5, the working fluid is pumped to the 0.6, and then going back to the steam generator. So steam generator here, it consists of the boiler and superheater. Then the working fluid is going back again to point number 1, and so on. So therefore this will be a kind of cycle. On the right side is the TS diagram. So point number 1, I believe this is a superheated vapor. So if you can also check using table A2 or A3, because this is water. So goes to table A2, and then looking at temperature 480 degrees C, and check what is the saturated pressure. If the saturated pressure is higher than 80 megapascal, okay, then the condition is superheated. Okay. Similarly, you can also use table A3. It is a pressure table, and check what is the saturated temperature at 80 bar. So if the saturated temperature is lower than T1, then the condition or the state at point 1 is superheated. So point 1 here is superheated, and then from point 1, the working fluid flows through the first stage turbine going to the point 2, and the point 2, the pressure is given there, it is 0.7, and then you need to check. So by coincidence here in the TS diagram, you see that point 2 is inside the dome, but you can also check it later on. In the actual problem in the exam, for example, you might not know what is the where is the location of point 2. It might be inside the dome, it might be outside the dome. Okay, so the way you check it is by comparing the entropy at point 2 And you can see there between point 1 and point 2 it is connected by a straight vertical line, and this is the entropy. So it's mean the entropy at point 1 equal to the entropy at point 2. Okay, so to check whether this point 2 is inside or outside the dome, compare the entropy at point 2 with SF and SG at this pressure. Okay. And for this example, S2 is lower than SG, therefore point 2 is inside the dome. Okay, and then from point 2 it is reheated by reheater going to point 3, and from point 2 to point 3 the process occurs at the same pressure. So you can see there you have let me use a different color. So this is the constant pressure line, so P2 equal to P3. Okay, and then from point 3 to point 4 the working fluid flows through the second stage turbine. Similarly, in this case we know that state number 4 is inside the dome, but in other case like the exam or homework you need to check it. The same thing like when you check point 2. So compare the entropy at state number 4 with SF and SG at this pressure. Okay, good. And then inside the condenser there will be a heat transfer from the working fluid to the environment. Therefore state number 4 here is changed to state number 5. Okay, between number 4 and number 5 they have the same temperature, but the energy decreases because there is a heat transfer out of the working fluid. And then from number 5 to number 6 the working fluid is pumped, so that the pressure increases here. From number 6 it's flow through the steam generator, and then it's change the state from point 6 here back to point 1 and so on. Okay. Okay, this is the engineering model or assumption. First is that each component in the cycle is analyzed as a control volume at steady state. So this is the keywords: control volume and steady state. Okay. And then all processes of the working fluid are internally reversible. So it's mean there is no entropy production. In chapter 6, the entropy production is represented by the sigma. So sigma equal to 0. Okay. And then number 3, the turbine and pump operates adiabatically. So it's mean there is no heat transfer in these two components. Okay, turbine and pump. Number 4, condensate exits the condenser as saturated liquid. So it is represented by state number 5 here. Point number 5 here is exactly at the dome line on the left side. So this is saturated liquid. And number 5 here, we can neglect the effect of kinetic and potential energies. Okay, and then the next step is to determine the state properties for each point here. We can start with point number 1. So in the point number 1, pressure is given, temperature is given, and this is saturated vapor. This is water, so you need to use table A4. Okay, table A4, and I'm assuming in Thermo 2 you are proficient on reading the table, find out the properties and so on. So we need to look at this pretty quick. So using table A4, you will get H1 as well as S1 with this number. So H1 is 3348.4 kilojoule per kilogram, and this S1 is 6.6586 kilojoule per kilogram Kelvin. We'll use this S1 to determine the properties at state number 2. Will be the next slide. Okay, state number 2 is fixed by the given pressure, so 0.7 megapascal, as well as this one. The entropy at point 2 equal to the entropy at point 1. So you need to go to pressure table of water. It is table A3. This is SI unit, so you need to use table A3, not A3E. So goes to table A3 and then compare S2 versus SF and SG. So in this case, S2 is lower than SG, and for sure it is higher than SF. Therefore, 0.2 here is inside the dome. Then you can use the information of the S2, SF, and SG at 0.7 megapascal to calculate the steam quality. Okay. In this case, we have 0.9895. Once we have X2, then we can calculate H2. This one. So this formula, I believe, in chapter 3 or 4. Okay. Chapter 3. Yeah, H2 equal to HF. So this is the saturated liquid enthalpy plus X2 times HFG. HFG here is Hg minus Hf. I believe there is one column in that table showing HFG. This helps you to save a time. So instead of using calculator to calculate Hg minus Hf, so you can use the number in that corresponding column directly. So HFG at 0.7 bar. So plug in all the number here in your calculator and you will get H2 is 2741.8 kilojoule per kilogram. And then going to state number 3, temperature is given, pressure is also given, and you can check that state number 3 is superheated. So you need to go back into table A4 and you will get this H3 and S3. You will use S3 to help determine state 4. So in state 4, pressure is given 0.008 megapascal or 0.08 bar, and then S4 equal to S3. You do the same thing like what we did here to estimate X2 and H2. In this case, you need to estimate X4 and H4. Okay, so X4 is 0.9382. Okay, and then H4 is 2428.5 kilojoule per kilogram. And then state number 5, it is saturated liquid at 0.08 bar. So you use table A3. So this is pressure table for water. So H5 equal to HF at once again at this pressure. And then state number 6 here, it said that you can look at example 8.1. So I think the way it's worked there is you have to use an approximation here to estimate H6. Okay, so look at example 8.1 to check this number. Okay, so we have completed the state properties for all 6 points, and I think we are ready to go to answer the question. Okay, the first question is the net power developed by the cycle. So in this case, the net power will be the power from the turbine. So we have 2 turbines here. So we have 2 turbines. So the first stage turbine and the second stage turbine. So the power from the turbine will be the sum of these 2 turbines. And then to get the net, we need to subtract these powers by the power required by the pump. Okay, so the power developed by the first stage turbine is m dot times H1 minus H2. So H1 is the inflow enthalpy, H2 is the outflow enthalpy. Similarly, you have this formula for the second stage turbine, and then for the pump, you use this formula. Okay, and then the total rate of heat transfer to the working fluid, it is the Q in from the steam generator. So m dot times H1 minus H6. Okay, so this one. So from 6 to 1, here is the process inside the steam generator. And then you have the second Q in, which is the Q inside the reheater. So it is used to reheat the working fluid from state number 2 to state number 3. So this one. Okay, so to calculate the system efficiency, then the formula is the same. So what we gain over what we pay. So what we gain is the net power. What we pay is the Q in. So we have two Q in. So one is inside the steam generator and second one is inside the reheater. And you have all number here. So H1, 2, 3, 4, 5, 6, you have all number. You just plug in all the number in this formula, and then using your calculator you will get the efficiency. The efficiency is 40.3%. Okay, 40.3%. As I mentioned to you earlier, that in example 8.1, where the system doesn't have a superheater, doesn't have reheater, the efficiency was only 37.9%. So you see there is an increase of about 2.4% by having a superheater and reheater in this cycle. The second question is the mass flow rate of the steam. So the net power is given. So we can calculate the mass flow. So the net power is the mass flow time the power generated by the first turbine plus the power generated by the second turbine minus the power required by the pump. This one. And we have all number in the parameter on the right side here. So you just plug in and you will get the mass flow rate, 2.363 times 10 to the power of 5 kilogram per hour. And then question number 3 is the rate of the heat transfer from the condensing steam to the cooling water. So this one, Q out. So Q out here is just m dot times H4 minus H5. So m dot is calculated in the second question, and we have H4 and H5. Then you should be able to calculate Q out here. So once again, by having a superheater and reheater in this Rankine cycle, the efficiency increases from 37.9% to 40.3%. Okay, the next example, what will happen if we incorporate the effect of turbine irreversibilities on the previous cycle? So in this case, the turbine efficiency is 85%. And then you can see the TS diagram on the left side here. Because of these irreversibilities, the working fluid exits the turbine on the right side of the point 1 or on the right side of the point 3, which means the entropy at the turbine exit is higher than the entropy at the turbine inlet. So this point 1, if it is isentropic, which means adiabatic and internal reversible, so the point at the turbine exit is 2s, this one. But in reality, there will be a irreversibility inside the turbine, which make the entropy increases. Therefore, point 2, which is at the turbine exit, has a higher entropy than point 1. See here, horizontal line here represent the entropy. Similarly, on the second stage turbine, point 4s here is where we have no irreversibility inside the turbine and also no heat transfer. It means that from 3 to 4s, it is isentropic process. And then there is irreversibilities inside the turbine which make the entropy increases. So this is, we have state 4. And then you can see that the line for the actual process represented by the dash line. So from point 1 to point 2, or from point 3 to point 4, the line, the connecting line is the dash line. Okay, this is the engineering model. So the first assumption is the same. This is control volume at steady state. And then except for the two turbine stage, all processes are internally reversible. And then the turbine and pump operate adiabatically. And then state number 5 is saturated liquid, and we can ignore the effect of kinetic and potential energy. Let's take a look on the solution of this example. So state number 1 stay the same as the previous example. So we have H1, and then we have calculated H2S. So now we need to calculate H2. And you look at this on this TS diagram, point 2 is outside the dome, so it is a saturated vapor. So to calculate H2, we can use the turbine efficiency formula, this one. So H1, H2, S, and then turbine efficiency are given. Then you can calculate H2. And then similarly, you can calculate H4. So if you want to know the exact location of point 2 and point 4, for sure you need to check with the value of saturated liquid and saturatable at the corresponding pressure. For example, in this case, we know that H2 is outside the dome, and I think H2 is higher than Hg at 0.7 megapascal. So you can check it in table A3. Okay. Similarly, you can check H4, and looking at this TS diagram, H4 is inside the dome. So it means in this case is H4 is lower than Hg at 0.08 bar. Okay. So once we got H2 and H4, we can recalculate the thermal efficiency of the cycle. So this case, with 85% efficiency of the turbines, both turbines, so the thermal efficiency now is only 35.1%. So the previous example, when we don't have irreversibilities inside the turbines, the thermal efficiency was 40.3%. So there is around 5% thermal efficiency reduction due to irreversibilities within the turbines. Okay, the next topic for the system modification to improve the performance is by having a regenerative vapor power cycle. With regenerative feed water heating, the working fluid enters the boiler at stage between 4 and A. So without feed water heating, the steam or the working fluid enter the boiler at state number 4. Okay, and then by having the feed water heating, the working fluid enter the boiler between point 4 and point A, assuming it is at this point. Let's say this is point, let me put this one is point 4 prime. So in this case, now the average temperature of heat addition, which is TH, is increased. Why? The TH now is the average temperature between point 0.4 prime here and 0.1 prime here. Okay. Without feed water heating, the average temperature, so it is TH, is between 0.4 and 1 prime here. And once again, the Carnot efficiency for this Rankine cycle is 1 minus Tc over Th. So if the Th increases, it means that the thermal efficiency also increases. Okay, so thereby tending to increase the thermal efficiencies. Okay, there are two types of feed water heaters for this regenerative Rankine cycle. The first type of this feed water heater is called open feed water heaters. So this feed water heaters is a type of a direct contact heat exchanger. So it means the inflow stream will mix, okay, and then will exit at the single point. So once again, streams at different temperature mix to form a stream at intermediate temperature. In this case, this is the exit, 0.6. Okay, let's take a look on this schematic. So in a regenerative Rankine cycle, some of the working fluid is extracted at the intermediate pressure between the turbine inflow pressure and the last turbine outflow pressure here. So it is at pressure number 2 here. So only some. So and then the rest will flow to the second state turbine. Therefore, we will still have 2 turbines here. So the power of the turbine will be the sum of these 2 turbine powers. Okay, assuming we have a mass flow 1 here, okay, and then some of the working fluid is extracted and then goes to the open feed water heater. So let's say Y here represent the ratio of the mass entering the feed water heater from the turbine, and then the rest, which is 1 minus W here, will go to the second stage turbine. Okay, so and then the rest of the cycle is similar to the original Rankine cycle. So in this case, you have 2 pumps because first you need to pump the first working fluid here at state 4 going to state number 5 here, and then it's flow through the open feed water heater, and then the second pump will increase the pressure pump from the pressure at 0.6 here to the pressure of 0.7, which is the steam generator pressure. Okay, first the amount of the extracted mass here at state 2 as well as the amount of mass flow at 0.5 here is in such a way that at the exit of the feed water heater, the condition at 0.6 here is saturated liquid. Okay, so there will be a control there to adjust the mass flow at 0.2 and 0.5 as well as other parameter to make sure that at the exit of the open feed water heater, the stage is saturated liquid. And then if you compare with the previous modified Rankine cycle, you can see there that on the second stage of the turbine, the mass flow is reduced because some of the mass flow need to be flown to this open feed water heater. So there will be a reduction of this turbine power. So in a regenerative Rankine cycle, the operating condition is in such a way that the reduced fuel energy more than offset the reduced turbine power, and therefore the system efficiency increases. Okay, So why I say reduce fuel energy? Because when the steam enter the steam generator, the state is not at A anymore, but it is at 7. Okay, so it is at higher initial energy. So there will be a reduction of the fuel energy to heat up this water to produce the steam or to produce the superheated vapor. So once again, to make sure that the system efficiency increases, the operating condition is in such a way that the reduced fuel energy more than offset the reduction of the turbine power. This is the analysis for a regenerative cycle. So first is looking at the mass flow balance and then energy balance for the open feed water heater, this one. So you can see in here the inflow stream is M2 and then M3 M5 actually, but M5 here equal to M3, and then the exit stream is M6, which equal to M1. So you have this one. So M2 plus M3 equal to M1. Okay, and then Y is the amount of the extracted steam here going to the feed water heater here. Therefore, Y here is M.2 over M.1. And then if you divided each term on this formula by M1, M.1, you will have this equation. M.2 over M.1 plus M.3 over M.1 equal to 1. And then we can apply the energy balance for this open feed water heater. So in this case, we assume that there is no heat transfer out of the feed water heater going to the environment. So in this case, Q equal to 0 and then W for sure equal to 0. So the only energy form here is the enthalpy flow, the flow enthalpy. Sorry. And this is steady state, so there is no change of the energy inside the system. So in this case, we have the inflow. So the inflow enthalpy is from 0.2 plus the one from 0.5. So we divide each term here by M1, okay, and then the outflow enthalpy is from 0.6 here, okay. So you manipulate this formula slightly, and then you will get the formula for Y shown in this equation 8.6. So Y equal to H6 minus H5 over H2 minus H5. Further analysis of this regenerative cycle, the turbine powers is from both stage turbines. The first stage here is the M.1 time H1 minus H2, and then the second stage turbine here is M.1 time 1 minus Y here time H2 minus H3. And then we have two pumps, okay. It means the required power for pump, we have WP1 and WP2. And then here in pump number 1, the mass flow is M.1 times 1 minus Y. And then in the second pump, we have M.1. Okay, this formula, equation 8.14. And then for the Q in, so we have M.1 times H1 here minus H7. And then inside the condenser, Q out is M1 times 1 minus Y times H3 minus H4. Okay, let's take a look on this example for a regenerative cycle with open feed water heater. So consider a regenerative vapor power cycle with one open feed water heater. Steam enters the turbine at 8 megapascal and temperature 480 degrees C. I think this is state number 1, same as the state number 1 in the previous example. And then expand to 0.7 megapascal, same thing as well. Where some of the steam is extracted and diverted to the open feed water heater operating at 0.7 megapascal. Okay, so the open feed water heater pressure is 0.7 megapascal. The remaining steam expands through the second stage turbine to the condenser pressure of 0.008 megapascal, and then saturated liquid exceeds the open feed water heater at 0.7 megapascal. And then the isentropic efficiency of each turbine is 85%, and each pump operates isentropically. It means there is no irreversibilities inside the pump, and also Q equals to 0. If the net power output of the cycle is 100 megawatt, determine A is the thermal efficiencies, and then the mass flow rate of the steam, so in kilogram per hour. Let's take a look the solution of this example. Okay, what is known is a regenerative vapor power cycle operates with steam as the working fluid, and then operating pressure and temperatures are specified, and then the isentropic efficiency of each turbine and the net power output are also given. The question is the thermal efficiency of the system and the mass flow rate of the working fluid into the turbine in kilogram per hour. This is the schematic of the system. So same as the one in the previous slide. So we have two turbines, so first stage and second stage turbines. And then we have open feed water heater here. And this is the steam generator. Point 1 is entering the first stage turbine, and then point 2 is where the working fluid is extracted and then diverted to the open feed water heater. Then we have two pumps here, so everything is the same. And then the TS diagram is on the right side. So we have irreversibilities inside the turbine, so that we have a dashed line connecting point 1 to point 2, as well as between point 2 and point 3. This is the engineering model. So this is a closed system steady state. And then all processes of the working fluid are internally reversible, except for the expansions through the two turbines and mixing. Okay, so there is irreversibilities there. And then the turbines, pumps, and feed water heater operates adiabatically. Okay, and then we can ignore the effect of kinetic and potential energy. And then saturated liquid exceeds the open feed water heater. And then saturated liquid also exit the condenser. So you can see here 0.4 and 0.6 are at the dome line. So it means they are at saturated liquid condition. Okay, for the analysis, we start by determining the properties at each point. So we can start with point number 1. I think we have the number from the previous example, state number 1, as well as state number 4. Okay, and then state number 2, I believe we also have it already in the previous example. Okay, and then state number 3, we can calculate it from the correlation of the turbine efficiency. Okay, so pretty much the same as the one we did in the previous example. So we calculate H3, and then state 6, it is saturated liquid at 0.7 megapascal or 7 bar. So in this case, you need to use table A3. Table A3, and then look at HF. So HF here will be the H6 here. So 697.22 kilojoule per kilogram. Okay, and then you can calculate H5 by using this correlation, because the pump operates isentropically. So H5 here equal to H4 plus V4 times P5 minus P4. So V4 here is the specific volume. Okay, and then you can use table A3. So this pressure table goes to pressure of 0.08 bar. So you will get V4 with this VF, and then P5, P4 is given from the problem, and then H4 we calculated from the previous, we determined it from the previous example. Then you should be able to get what is H5. And then similarly, you can also calculate H7. Okay, and then from the formula of Y, which is the fraction of the working fluid extracted and diverted to the open feed water heater, so you can get the value of Y 0.1966. Then we are ready to answer the question. So first is the question is the thermal efficiency. So we need to calculate the net. We need to calculate the power developed by the two turbines using this formula. So through the first stage turbine, it is m.1 times h1 minus h2, and then through the second stage turbine, it is m.1 times 1 minus y times h2 minus h3. So you have all number for each parameter here, and you should be able to get this power developed by the two turbines. So 984.4 kilojoule per kilogram. And then you can do the same thing to calculate the power required by the two pumps. So this is m.1 times h7 minus h6, and then plus m.1 times 1 minus y times h5 minus h4, and you will get this number, 8.7 kilojoule per kilogram. And then Q in is m.1 times h1 minus h7, so you get this one, 2643.1 kilojoule per kilogram. And based on this three value, you get the thermal efficiency of this regenerative Rankine cycle, 36.9%. Okay, 36.9%. I think it is higher than the one from the last example. So I believe it is like 35 point something percent. So you can see there is an increase of the efficiency by having a regenerative Rankine cycle. And then the mass flow rate here, so you do the same thing like in the previous example. So we have the net power here, which is turbine power minus pump power, and we have the turbine power, we have the pump power per kilogram of the working fluid, and then you just plug in all the number, you should be able to get this mass flow rate, 3.69 times 10 to the power of 5 kilogram per hour. The second type of the feed water heater, what is called closed feed water heater. This closed feed water heater are shell and tube type recuperators in which the feed water temperature increases as the extracted steam condenses on the outside of the tubes carrying the feed water heater. So look at this schematic. So we have the extracted steam in this side, and then the feed water flows through the tube. So this is the tube, and then the temperature increases. Okay, the temperature increases as this extracted steam condenses, so that you can see the condensate at the bottom of this feed water heaters. And then because these two streams do not mix, the pressure level between the extracted steam and the feed water heater can be different. Okay, can be different because they do not mix. Then there are two scenarios for the condensate. First, on the left side, either this condensate will be pumped to higher pressure line, or this condensate going to the right side feature here will be diverted and then flow through the steam trap, which is a kind of a throttling process. So then the pressure will drop to the lower pressure heater or condenser pressure. This is the schematic of a Rankine cycle with a closed feed water heater. So state number 1 stay the same there at the entrance of the first stage turbine, and then we have stage 2 here, okay, and then state 3 is at the exit of the second stage turbine, and then flow through the condenser, state number 4, and then it's pumped to state number 5, and then this is the closed feed water heater. The condensate will be diverted and then flow through the trap here, so that the pressure drop to 0.8, which is the pressure of the condenser. So inside the condenser, state number 8 here will mix with state number 3, okay, and then at the exit of the condenser will be a saturated liquid. See here, number 4. Okay, and then back again to the pump process here. From state number 4, it will be pumped to state number 5, and then the feed water will get heating from the extracted stream, and it's go to state number 6 here. And then from the 6, it flows going into the steam generator, and then back again to state number 1. And the TS diagram is on the right side there. And we have one process with the dash line. So this is the throttling process. So throttling process is always irreversible process. So therefore we have a dash line here. And this is the formula that we have for this open feed water heater, especially the one to estimate Y. So this is the fraction of the extracted working fluid. Okay. So Y equal to H6 minus H5 over H2 minus H7. Some vapor cycle can have a multiple feed water heaters as shown in this figure. So we have 1, 2, 3. We have 3 closed feed water heater and then 1 open feed water heater here. So by having multiple feed water heaters, system efficiency increases. But you can see there we have more components, which means that the capital cost also increases. And then in case of multiple feed water heaters, at least one open feed water heaters operating at a pressure greater than atmospheric pressure is needed. In this case, we need to fan oxygen and other dissolve out of the system. And the process of this gas venting is called deaeration. Let's have a look on this example. So we have a reheat, a regenerative cycle with a 2 feed water heater. So slightly complex system here. So consider a reheat regenerative vapor power cycle with a 2 feed water heater. So we have 2 feed water heater, a closed feed water heater and an open feed water heater. Steam enter the first turbine at 8 megapascal and temperature of 480 degrees C. This is state number 1. I believe this is the same as the state in the previous examples. and expand to 0.7 megapascal. This is also the same. The steam is reheated to 440 degrees C before entering the second turbine, where it expands to the condenser pressure of 0.008 megapascal. This is also the same. Steam is extracted from the first turbine at 2 megapascal, as new one, and fed to the closed feed water heater. Feed water leaves the closed heaters at 205 degrees C and 8 bar megapascal, and condensate exits as a saturated liquid at 2 megapascal. The condensate is trapped into the open feed water heater, so it's trapped, so it's going to the lower pressure level. Steam extracted from the second turbine at 0.3 megapascal is also fed into the open feed water heater, which operates at 0.3 megapascal. And then the stream exiting the open feed water heaters is saturated liquid at 0.3 megapascal. The net power output of the cycle is 100 megawatt. This is also the same as the previous one. There is no stray heat transfer, so it's just a heat transfer, no heat transfer from any component to its surrounding. If the working fluid experiences no irreversibilities as it passes through the turbines, pumps, steam generator, reheater, and condenser, determine. First question is thermal efficiency, and then the mass flow rate of the working fluid in kilogram per hours. The question are also the same here. What is the thermal efficiency of the system and what is the mass flow rate? Okay, let's take a look on the solution of this example. This is the schematic of the system, and then the TS diagram is on the right upper side of this slide. So step number 1 is the entrance of the turbine here. So this is step number 1. So temperature and pressure are given, and then you see there are several stages of the turbine. So this is the step number 2. Some of the working fluid is extracted going into the closed feed water heater. So the amount of this extracted steam is represented by this fraction number, so it's y prime. And then exiting this turbine, it is step number 3, and the working fluid is reheated inside the reheater, and then it goes to step number 4 here at the exit of the reheater, and then going back again to the other stage of the turbine, and then there is a working fluid extraction here, second extraction of the working fluid. It is step number 5. It's going to the open feed water heater, and the amount of this extracted working fluid is represented by this Y with quotation sign here. Okay, and then exiting the last turbine stage, it is step number 6 here, and then it flows through the condenser at the pressure of 0.008 megapascal. There will be a heat transfer going out of the working fluid when it flows through the condenser, and then 0.7 here is the exit point of the condenser. This is saturated liquid, and then this condensate is pumped by pump number 1 here to the open feed water heater. So this is step number 8, and then this fluid mixed with the extracted fluid from step number 5 here, and the amount of this two stream is in such a way. Oh, wait a moment, we also have another stream coming in to the feed water heater. This is step number 13. So the operating condition, which is the
pressure, temperature, and mass flow of these three streams is in such a way that at the exit of the open feed water heater, the fluid state is saturated liquid, represented by 0.9. Okay, and then this condensate is pumped by pump number 2, going into state number 10, and then it mixed with the extracted working fluid, state number 2, going, oh sorry, it doesn't mix. This is closed feed water heater. Okay, so 10 working fluid at point 10 got heated from the extracted fluid, okay, from the extracted fluid, and then it increases the temperature from state 10 to state 11, this one, okay, and then by looking at the extracted fluid from state number 2, because there is a heat transfer from this extracted fluid inside the closed feed water heater, the state of this extracted fluid changed from state number 2 into state number 12. And state number 12 here, it is a condensate, and this is a saturated liquid condition. So it is on the dome line on the left side. See here, this is state number 12 in the TS diagram, you can see there. Okay, so we have 13 point here, 13 operating point here. So from 1 up to 13. And then there is one process with the dash line. This represents the process line connecting state 12 and state 13. So this is the process inside the trap here. So this is a throttling process. So there is irreversibilities inside this throttling process. Therefore, the line connecting state 12 and 13 is represented by a dash line there. Okay, so the TS diagram is shown on the right upper side of this slide. So we have state number 1. So this is a superheated state. So temperature is given, pressure is given, and this is water. So you will need to use table A4. So this is SI unit, so A4. And then state number 2, I think the pressure is given 2 megapascal, and the entropy at state 2 equals to the entropy at state 1. And then you can check where is the location of state number 2. If S2 is larger than SG at 2 megapascal, then the state 2 is on the superheated side. Otherwise, it will be inside the dome. Okay, state number 3, the pressure is given there, and the entropy of state number 3 equals to the entropy at state number 1. You can see on this TS diagram, the line connecting state 1 to 3 is a straight vertical line. So it's mean the entropy of these 3 points is the same. And then there is a heating from state 3 to state 4, and the process occurs at the same pressure. And you can see in the TS diagram that the line connecting point 3 and point 4 is a constant pressure line. And then at point 4, the temperature is given 440 degrees C. And then you can check easily that at this 0.7 megapascal and 440 degrees C, the state of the working fluid is superheated condition. And then from state number 4 to state number 5, the entropy stays the same. You see there the straight vertical line connecting these 2 points. So you can check from the table what is the state of this point number 5. So same thing like what we did when we would like to check what is the state of point 2. So the pressure at 0.5 is 0.3 megapascal or 3 bar. So you can check whether S4, which equal to S5, is higher or lower than SG at 0.3 bar. Okay, and then state number 6 has the same entropy as state number 4, and the pressure is 0.008 megapascal or 0.08 bar. And according to the TS diagram, for sure you can check it that state number 6 is inside the dome. And then state number 7, it is assumed that it is saturated liquid, so state number 7 is right at the dome line on the left side. And then 7 to 8, it's pump. So for the isentropic process, so it's connected by a straight vertical line. So state number 8 is in the compressed liquid zone there. And then 8 to 9, so 9 here is at the exit of the open feed water heater. So the working fluid at state number 5, and then state number 8, and then state number 13, mix, and the final state here is at 0.9 here. Okay, once again, as I mentioned to you, the operating condition for this 3 point, 0.5, 0.13, and 0.8 is in such a way that at the exit of the feed water heater, this open feed water heater, is a saturated liquid, state number 9. And then from state number 1, it is pumped to state number 10, so it is isentropic process. And then from 10, it's enter the closed feed water heater. There is an incoming energy to this working fluid, so that it's changed from state number 10 to state number 11. Okay, so state number 11 has a higher energy. And then from 11, it's going back again to the steam generator, and then state number 1, and so on. Therefore, this working fluid undergoes a thermodynamic cycle. Okay, this is the engineering models or assumption. So number 1 here, that each component is a control volume, and then it is at steady state, and then the boundary of the control volume is represented by a dashed line, and then there is no heat transfer from any component to its surrounding. So all process inside the turbines, pumps, and then feed water heater is adiabatic process. And then number 3, the working fluid undergoes internally reversible process. It's passed through the turbines, pump, steam generator, reheater, and condenser. So especially for the pump and turbines, this is adiabatic and also internally reversible. So it means it is an isentropic process. And then number 4, the expansion through the trap is a throttling process. So it means the enthalpy stay the same. And number 5, we can ignore the impact of kinetic and potential energies. And number 6 is the assumption that condensate exceeds the closed feed water heater, a saturated liquid at 2 megapascal. And then feed water exit the open feed water heater, a saturated liquid at 0.3 megapascal. Also condensate exit the condenser, a saturated liquid. So if you look at the TS diagram at the bottom here, we have state number 7, 9, and 12. All are at the dome line on the left side of the dome. Okay, the next step is to determine the state properties. We can start from state number 1. So from state number 1, temperature and pressure are given. And then we know this number from previous example. So pressure is 8 megapascal or 80 bar, and the temperature is 480 degrees C. Using table A4, you should be able to get H1 and S1. And then going to state number 2, pressure is given, and then S2 equals to S1. And then you need to do an interpolation here to get what is the enthalpy at state number 2. And you will get this one, 2963.5 kilojoule per kilogram. And then the state at the exit of the first turbine is the same as at the exit of the first turbine of example 8.3. Oh, okay, so for state number 3 here, you can get the number from previous example. So H3 here is 2741.8 kilojoule per kilogram. And then state number 4, pressure is given, temperature is given, and then you can check it with either table A2 or A3 whether it is superheated or inside the dome. But by looking at this TS diagram, for sure it has been checked that state number 4 is in the superheated zone, and you need to use table A4 to catch the enthalpy as well as the entropy. So we got H4 here is 3353.3 kilojoule per kilogram, and then the entropy is 7.7571 kilojoule per kilogram Kelvin. And then we go to state number 5. Pressure is given 0.3 megapascal or 3 bar, and then S5 equal to S4. And then in this case, you need to do an interpolation to get the enthalpy at state number 4. And lastly, on the right side of the process line, we have state number 6 here. So S6 equal to S4, and then the pressure is also given 0.08 bar. And you need to apply the formula to estimate the properties inside the dome to get the enthalpy at state number 6. So once again, entropy at 0.6 equal to the entropy at 0.4, and then you can estimate the steam quality at 0.6, and then once we get this steam quality, we can calculate the enthalpy using this formula. So HF plus X, this is the steam quality, time HFG. So HF and HFG are evaluated at saturated pressure, so which is 0.08 bar, and you will get H6 of 2428.5 kilojoule per kilogram. And then state number 7, so this is at saturated liquid at 0.08 bar, so you need to use table A3 to get H7. So it's shown here, 173.88 kilojoule per kilogram. And then from 7 to 8, this is the process inside the pump. The process is an isentropic process, and you can use this formula to estimate the enthalpy at the pump exit. So H8 equal to H7 plus V7 times P8 minus P7. And V7 here is the VF at 0.08 bar. Okay, so P8 is 0.3 megapascal or 3 bar, and then P7 is 0.08 bar, and you will get H7 of 174.17 kilojoule per kilogram. Okay, and then the next state here is at 0.9, so this is saturated liquid at 3 bar or 0.3 megapascal. So you need to go to table A3 to get this H9. So H9 is HF at 3 bar. So you will get 561.7 kilojoule per kilogram. Then to get enthalpy at 0.10, so you can use the same formula as the one we used to get the enthalpy at 0.8. So H10 equal to H9 plus V9, this is VF, okay, V9, this is VF at 3 bar, times P10 minus P9, and you will get H10 here is 569.73 kilojoule per kilogram. And then going to state, okay, we are at state number 10. And then another information here is state number 12. State number 12 here, saturated liquid at 20 bar. So you need to use table A3. You will get H12 is 908.79 kilojoule per kilogram. And then the fluid passing through the trap undergoes a throttling process. So throttling process from state point 10 to point 13. So it's mean the enthalpy at point 13 equal to the enthalpy at point 12. So which is 908.79 kilojoule per kilogram. And then what is the missing one here? Oh, state number 11. State number 11 here is the point at the exit of the feed water heater, right? Okay. So state number 11 here, we have pressure of 8 megapascal and temperature of 205. And state number 11 here is on the left side of the dome. So it means it is inside the compressed liquid zone. Either you can use table A5, okay, either you can use table A5, or you can use this formula to estimate enthalpy at 0.5. So this is the enthalpy at the saturated liquid of the at the corresponding temperature, so 205, and then plus VF. VF here is the specific volume at the saturated liquid at the corresponding temperature, 205 degrees C, times the corresponding pressure, so P11, which is 8 megapascal, minus saturated pressure at the corresponding temperature. So in this case, the saturated pressure at 205 degrees C is 1.73 megapascal. And then you should be able to get this H11. It is 882.4 kilojoule per kilogram. Okay, so we have got all properties here. Which moment there is also information. Oh yeah, as I mentioned to you, either you use this formula or you can use table A5 to estimate the enthalpy at point 11. So we have got all state properties here, and we are ready to see or to get the solution for each question. So, oh, okay, so there is one more thing here. We need to determine what is the y prime and y double prime, or y with quotation here, using the formula from the previous slide. So the y prime here is the first x, I think the, let it on, so y first. So, okay, the y prime here is the extracted steam going into the closed feed water heater. Okay, and you apply the formula from the previous slide, you will get this y prime as 0.1522, and then the second extracted working fluid going into the open feed water heater. This is y double prime, or y with quotation mark here. And then you apply the energy balance of the open feed water heater, and then you should be able to get the y double prime. The first question is, what is the thermal efficiency of the system? So first we need to calculate the power developed by the turbines. We have two stage turbine. On the first stage turbine, so some of the working fluid is extracted going to the feed water heater. Therefore, we have this formula. So the first stage turbine power is m.1 times h1 minus h2, okay, and then plus m.1 times 1 minus y prime, because some of the working fluid has been extracted to the feed water heater, so we have less working fluid going to the next one. So times h2 minus h3. So you just plug in all number using your calculator, you should be able to get this one. And then for the second stage turbine, so same thing, we have m.1 times 1 minus y prime times h4 minus h5. Okay, so this one, h4 minus h5 plus m.1 times 1 minus y prime minus y double prime, because some of the working fluid was extracted to the second feed water heater. Therefore, we have minus y double prime here times h5 minus h6. So here. Okay, so we have all number, and then you plug in, you will get the power generated by the second stage turbine. So we have the turbine powers. Now we are going to the power required by the pump. So we have two pumps. The first pumps, here we use this formula. So it is m.1 times 1 minus y prime minus y double primes times h8 minus h7. So we have 0.22 kilojoule per kilogram. For the second pump, so I believe on the second pump, here all fluid amount should be included there. Therefore, we have m dot, and times directly here is h10 minus h9. So we don't have any y parameter in the second pump. So, and then plug in all the number, we have the power required by the second pump is 8.26 kilojoule per kilogram. The next one is to calculate the Q in. So we have a steam generator, and then we also have a reheater. Okay, so the first Q in is used to heat up the working fluid from state number 11 to state number 1. So we have this one. And the second Q in is required by the reheater to reheat the working fluid from state number 3 here to state number 4. We have this one. Okay, by plugging all the number and use your calculator, you will get the total Q in is 2984.4 kilojoule per kilogram. So we have the turbine power, we have the pumping power, and we have the Q in. Then we can calculate the thermal efficiency of the system. In this case, we get 43.1%. So if you compare this number with the thermal efficiency from the previous number, I believe this is the highest one. So in this one, we have more complex system. We have regenerative system here with 2 feed water heaters, and then we still maintain having a reheater and superheater. And you can see in this example that the thermal efficiency increases to 43.1%. But for sure, you will expect an increase of the capital cost to build this system. The second one is to calculate the mass flow rate. So the way we calculate it is the same as the way we did from the previous example. So the net power is given 100 megawatt, and then we already have the turbine power and the pump power. And what is important here that you need to pay attention is the unit conversion. It is megawatt, so you need to make sure that all units are comparable here. So megawatt, and then here there is one conversion here where you need to change from second to hours, and then the second one is to convert the unit from megawatt to kilowatt. So you will get this number. So the mass flow rate is 2.8 times 10 to the power of 5 kilogram per hour. The next topic is cycle aspect. So the first aspect we look at here is the working fluid. So most of the steam vapor power use water. So in this case is demineralized water as the working fluid because of plentiful and then low cost, non-toxic, chemically stable, and relatively non-corrosive. So water is the most popular working fluid for the power plant. And then other working fluid is also available outside there, including pentane, and then mixture of hydrocarbon, and then ammonia, silicon oil. So each of this working fluid has its own characteristic, and the main characteristic here is the low temperature operating condition, which will be helpful when we talk about a binary vapor cycle, or which will be helpful in case we have a different source of the energy. For example, if we want to utilize the waste energy from the industrial, which have lower temperature, maybe in the order of 300 degrees C, 400 degrees C, then you might need to use a different working fluid that has a lower temperature characteristic like ammonia or hydrocarbon. The next aspect is what's called a binary vapor cycle. So in this binary vapor cycle, it couples two vapor cycles so that the energy discharged by heat transfer from one cycle, which is the top cycle, is the input for the others, which is the bottom cycle. So in this case, we need to use a different working fluid. So the first one should be a working fluid with a high temperature characteristic, and the second one should be the working fluid with the low temperature characteristic. And then by having this binary vapor cycle strategy, the thermal efficiency is greater than either cycle has individually. This is the schematic of the binary vapor cycle. So there are two Rankine cycle, or there are two systems here. On the left side, this is high temperature cycle. So the main components stay the same as the one I showed you in the previous slide. So we have steam generator here, and then we have a turbine, and then this one, this side, acts as the condenser for the high temperature cycle, and this is the pump, and then going back again to the steam generator. And then we have the second cycle here, which is a low temperature cycle. And for the low temperature cycle, this part acts as the steam generator, or maybe not steam, or maybe yes, steam, because this is a low temperature characteristic working fluid. So this one can be a boiler or steam generator. And then you can see in here, it going also into this part of the steam generator from the high temperature system, and then exiting this steam generator we have a vapor, and then going into the turbine, this condenser, pump, and then recirculate back to this heat exchanger. And this is the TS diagram. So we have completely two different cycle here. The first cycle, it's called topping cycle here. This is high temperature cycle. So we have the process from state number 1. It is at the entrance of the turbine, and then going number 2, 3, 4, going back again to number 1. And then the low temperature cycle, which is also called bottoming cycle here. We have state A, and then B, C, D, E, and back again to A. And you can see the line here, the two line, horizontal line, connecting state 2 to state 3. So this is actually the process inside the condenser of the high temperature cycle. And then the horizontal line connecting E, and then let me put here is D prime, connecting E and D prime, and then D here. This is the process of the Q in. So Q input to the working fluid of the low temperature cycle. So there is a heat transfer here. Okay, so by having this binary vapor cycle, once again, the system efficiency increases compared to the one operate individually. The next aspect is what is called cogeneration. So in this case, the Rankine cycle is designed to produce two valuable products. One is the electricity, so it's coming from the turbine power coupled to the generator, and the second one is the steam. Okay, so the steam is produced through this condenser. So you know the condenser term out the heat transfer, and this heat transfer is transferred to the condensate, and then it will produce steam, and the steam will be rotated to the community. So this is a popular system, especially in the area where they have, for example, like a winter, strong winter season, like in New York or in the northern part of the United States. And this cogeneration type is called back pressure plant because we can adjust the amount of the steam energy here by adjusting the pressure at point 2. Okay, so if you want to have high steam temperature, we need to have the pressure at state 2 so that the settled temperature at that pressure is higher than the targeted steam temperature here. For sure, by increasing the pressure at point 2, the turbine power decreases. The second option is what it's called extraction plant. So you see in this schematic, we have point 1 entering the turbine, and then some of the working fluid here is extracted, so represented by this Y. So this is the fraction of the extracted working fluid. So some of this extracted working fluid is diverted to this heat exchanger, and it is dedicated to produce the steam. Okay, so and this steam will be routed to the community. So still we have electric generator here, electric generator, and we also have a steam produced by this cogeneration plant. The next aspect is carbon capture and storage. As you might know that power plant using coal is one of the major source of CO2. So, and we know that CO2 in the atmosphere contribute to the global climate. This is also a hot topic, especially when we discuss about electric vehicle. So if the source of the electricity coming from the coal combustion, I think the global CO2 emission in the earth increases. Yes, the electric vehicle is a clean vehicle. It produces zero CO2, but this means that we might shift the CO2 production from San Antonio or from New York City or from Dallas, from Houston to the area where the power plant using coal is built. Okay, therefore, if you want to do a detailed or thorough analysis of the CO2 production using electric vehicle, we need to include the whole system, not only looking at the electric vehicle by itself, but also including the system upstream of the electric vehicle. Okay, back again to this topic. So CO2 production by the coal combustion is the main source of the CO2 emission in the world. So if you look at outside there are a lot of mitigation effort to minimize the CO2 production. So one of this is for sure by increasing the efficiency of the system. So if you increase the efficiency of the system, so it's mean for producing the same output power, it will require less coal. So it's mean it will also produce less CO2 emission. The next effort is by using a green energy source. It's called green here because it is renewable. So like the energy from the waterfall, from I think solar also. And the next one is here, the mitigation effort is by having a CO2 storage. This feature is showing an example of the method to store CO2 underneath of the earth. So in here you can see there is a CO2 injection, and it's injected to some layer of the earth. So you see here the CO2 stored in salty aquifer, and then there is also CO2 storing in unminable coal steam, and there is also here CO2 stored in depleted oil and gas reservoir. But still there's a question here, like whether this CO2 storing impact the other thing inside the earth, and also what is the lifetime of the CO2, whether they will stay there all the time, or it might diffuse around this storage area. So there's still a question mark there. Okay, the last topic of this chapter 8 is Exergy accounting of a vapor power plant. So the Exergy entering a power plant is with the fuel. So here, this is the Exergy that we pay, fuel. Okay, and then there will be a combustion there. It is a combustor unit here. There will be a combustion, and then there is a transfer energy from this thermal energy to the energy of the working fluid here, and then some of the energy will exit this system going to the environment. So we have several sources of irreversibilities inside the vapor power plant, and one of this source, which is the highest, is inside the boiler. And the boiler itself here, once again, consisting of combustor unit and then boiler itself, and if it has a superheater, and sometimes it's called steam generator. And the irreversible heat transfer occurring between the hot combustion gas and the working fluid of the vapor power cycle. So this is the main source of the irreversibility, and also the combustion process itself is the source of the irreversibility. Let's take a look on the example to give us more understanding on the Exergy analysis of the Rankine cycle. First is to analyze the Exergy analysis within the heat exchanger. So this heat exchanger is the boiler itself. So looking at back of example 8.2, so this heat exchanger has a stream of water entering at 8 megapascal, and then exiting the boiler as a saturated vapor at 8 megapascal as well. And then in a spread stream, we have a gaseous product of combustion, cool at a constant pressure of 1 atmosphere from 1107 to 547 degrees C. And then the gaseous stream can be modeled as air with ideal gas formula, and then T0, so the reference temperature and reference pressure. So here is given 22 degrees C and 1 atmosphere. The question is determine the net rate at which Exergy is carried into the heat exchanger by the gas stream in megawatt. And second question is the net rate at which Exergy is carried from the heat exchanger by the water stream. And then the question number 3 is the rate of Exergy destruction. And the last question is the exergetic efficiency. Let's take a look on this solution. So what is known here is a heat exchanger, and then has a water stream entering and exiting at known state, and we have a spirit gas stream entering and exiting at known state as well. And then what we need to find out is the Exergy carried out into the heat exchanger, and then Exergy carried from the heat exchanger, and then the rate of Exergy destruction. And the last question is the exergetic efficiency. This is the schematic of the heat exchanger. So we have two streams here. One is the gaseous stream, second one is the steam stream. And this is the assumption of the model. So this is control volume. There is no heat transfer between the heat exchanger to the environment. So this one is 0. But there is a heat transfer from the gaseous to the steam here. So inside it is not 0. Okay. And then we can assume that there is no work, and then kinetic energy and potential energy effects are neglected, and then we can model the combustion product as air, ideal gas. And then assumption number 4, the air and the water each pass through the steam generator at constant pressure. So there is no pressure drop in this problem. And then, I think we miss this number in the example. Number 5, only 69 of the Exergy entering the plant with the fuel remains after accounting the stack loss and combustion Exergy destruction. Okay, so it's mean about 31% of the Exergy here loss either going to the environment through the stack or because of the Exergy destruction inside the combustion process. And assumption number 6 here is that T0 and P0 is 22 degrees C and 1 atmosphere respectively. So first is we're looking at the conservation of mass principle inside the heat exchanger. So from the gaseous stream, air, so we know that the mass flow in equal to mass flow out. Similarly, we have mass flow in equal to mass flow out for the water stream. And then this formula is the energy balance inside the heat exchanger. So Q0 and then W0, and then this is the change of the flow energy from the gaseous stream balanced by the change of the flow energy from the water stream. Okay, and then we can modify this formula to get this one, that the ratio of the gaseous mass flow to the water mass flow equal to H1 minus H4 over Hi minus He. Okay, so Hi here is the inflow enthalpy of the gaseous, He is the outflow enthalpy of the gaseous. Okay, and then H1 is the inflow, and H1 is the outflow enthalpy of the water stream, and then H4 is the inflow enthalpy of the water stream. So the next one is to calculate or to estimate or to determine the enthalpy. So for the gaseous, this is air. So you need to use air table. This is table A22. And in this case, you only look at the temperature. So you will get the inflow enthalpy of 1491.44, and then the outflow enthalpy is 843.98. And then on the water stream side, we know the pressure. Okay, we know the pressure of 8 megapascal. The temperature is also given, I believe. So we can get the enthalpy at state number, wait, I think state number 1, this is saturated vapor, right? And then state number 4, this is liquid at this 8 megapascal. Okay, yeah, I need to correct my statement. Once again, state number 4, this is a liquid at 8 megapascal. And then state number 1, this is a saturated vapor, okay, at the same pressure at 8 megapascal. So you can use table A3 to get enthalpy at 0.1, and then you can use for state number 4, this is a liquid. I think you can assume this is a saturated liquid, and you can use the same table A3, to get H4, and you will get this one. Okay. And then there is also information here from example H.2 that the m dot for the water stream is 4.449 times 10 to the power of 5 kilogram per hour. And then by using this ratio number, we can calculate the mass flow of the gaseous stream. So this is 3.977 times the mass flow of the water stream. Okay, let's take a look on the solution of the first question. So the first question is the net rate at which Exergy is carried into the heat exchanger by the gaseous stream. So in this case, we use this formula, m dot A times the flow exergy entering the heat exchanger minus the flow exergy exiting the heat exchanger. Okay, and use this formula. So if you want to review again about this formula, go to chapter 7. Okay, so this is air and can be assumed behave as an ideal gas. So you can replace this entropy change by this formula, and we don't have the second term, which is R time ln pressure difference. So in this case it is Pi over Pe, because Pi equal to Pe, so this is 0. Therefore you only have this term to calculate the entropy difference. Okay, using the same table A22 for air, you should be able to get SI and SE in degree here, and you will get this number, that the net rate at which Exergy is carried into the heat exchanger by the gaseous stream is 231.28 megawatt. Second question is the net rate at which Exergy is carried out of the boiler by the water stream. So we use the same formula, but in this case it is for the water side. So we have H1, H4, and then using the same table, you can get S1 and S4. Okay, in this case, you use table A3 because pressure is given there. And then you should be able to get H4 and S4. In this case, they said that you need to use a double interpolation, okay, to get this one. Table A5 is the compressed liquid table. Okay, so you just need to plug in the number. You should be able to get the net rate of Exergy carried out from the boiler, 130.53. Okay, so you can see in here the Exergy going into the heat exchanger is 231.28, but the exergy that is carried out by the water stream is only 130.53. So the difference here is because of exergy destruction inside the heat exchanger. Okay, and this is the exergy destruction. So this is just the difference between the two numbers in answer A and B. So we have 100.75 megawatt exergy destruction. And then the exergy efficiency here is just the ratio between the exergy received by the water stream over the exergy provided by the gaseous stream. So the exergetic efficiency here is 56.4%. Okay, but keep in mind that only 69% of the exergy entering the plant with the fuel is assumed to remain after the stack loss and combustion exergy destruction. Okay, so in this case, you need to also consider this number. Okay, you need to consider this number so that we can conclude that 0.69, so it means this is 69% of the exergy, and then times 43.6%. So this is the exergy loss. Okay, so if you multiply these two numbers, you will get 30%, and this is the actual number of the exergy that is destroyed within the heat exchanger. Once again, by looking at this percent, you see that 43.6% of the exergy is destructed, but by looking at the additional information here, that only 60% of the exergy stay in the heat exchanger. So you need to multiply the percent of the exergy destruction, 43.6% times this 69%. So you get 30% here. So this is the actual exergy amount that is destroyed within the heat exchanger. The next example is analyzing the exergy inside the turbine and pump. Once again, we use the same data from the first example, example 8.2. And then T0 is 22 degrees C and P0 is 1 atmosphere. And then let's see the analysis of this exergy. And on the left side is the schematic of the system. The state at point 1 is given here. It is 8 megapascal at saturated vapor. And then state 2 is inside the dome. And then you can see here there is a dashed line in the TS diagram. So it means there is irreversibilities inside the turbine. And then for the pump, it's entered at point 3. This is a saturated liquid. And then at the pump exit, state number 4. And because of irreversibilities inside the pump, state 4 is on the right side of state 3. So it means S4 is larger than S3. And this is the engineering model. So I think it's pretty much similar to the one we have in example 8.2, except there is additional information here that only 69% of the exergy entering the plant with the fuel remain after accounting for the stack loss and combustion exergy destruction. And this is the data for the reference condition, so T0 and P0. So first is we can use this formula to estimate the exergy destruction inside the turbine because it is straightforward. So we have the m dot, we know T0, and then S2 and S1 I believe has been calculated in example 8.2, and then we can just plug in the number. You will get the exergy destruction inside the turbine. Okay. Similarly, you can do the same thing to calculate the Exergy destruction inside the pump. So this m dot times T0 times S4 minus S3, and you will get 0.11 megawatt. And then since only 69% of the entering fuel Exergy remain inside the heat exchanger, you need to multiply the number there. Okay, you need to multiply the number there, or you need to account for this number to estimate the actual Exergy destruction. So in this case, we can estimate the Exergy destruction. First is inside the turbine. So the Exergy destruction here is the ratio of this number over this one is the flow Exergy inside the turbine. Okay, and we have 7.23%. Okay, so once again, in this case, we have the Exergy destruction inside the turbine, and then we divide this number by the Exergy supplied by the gaseous, by the hot gas. This is 231.28, and then we will get 7.23%, and then we need to multiply it by the 69% because this is the actual fuel Exergy. Okay, so in this case we have 5% of the Exergy destruction inside the turbine, and similarly you can do the same thing for the pump. Then you will get, here the number is, let me check, so we have 0.03%. this is the Exergy destruction inside the pump, so it's pretty small. Okay, so it's mean we can assume that this is 0. The next one is Exergy analysis inside the condenser. So inside the condenser, we know that the fluid enter the condenser as the two-phase liquid vapor at 0.008 megapascal, and then it exits the condenser at saturated liquid at the same pressure here. Okay, and then the question, I believe, is similar to the previous one, so we need to determine the net rate at which Exergy is carried from the condenser by the cooling water, and then we need to express this one in terms of the fuel Exergy. Let's see the solution of this Exergy analysis. So condenser, this is a kind of heat exchanger. So there are two streams here. One is the stream from the working fluid itself, and the second one is the stream from the cooling water. And this is the assumption, pretty much similar to the previous one, except that we have additional assumption in 0.3 and 0.4 here. Okay, for A here, the net rate at which Exergy is carried out of the condenser, we can use equation 7.18. So this is the Exergy carried out by the cooling water. So it is this side. And this is the formula. So it is the mass flow of the cooling water times the flow Exergy difference between exit and inlet. And we can replace this formula, this one by this one. So we have all number, I believe, from the previous example. You just plug in, then you will get this number. 2.23 megawatt is the Exergy carried out of the condenser by the cooling water. Okay, and then if you make the ratio between this one and the Exergy entering the system by the hot combustion and then multiplied by 69%, so you will get 1%. So this is the Exergy carried out of the condenser by the cooling water. And then the second one here is to estimate the Exergy destruction for the condenser. And we have this formula. So this is T0 times m dot times the entropy difference between state 3 and state 2. So this is from the working fluid side, and this one is from the cooling water side. And you have all number, you just plug in and you will get 11.56 megawatts. So this is the Exergy destruction inside the condenser. And then if you ratio this number by the Exergy entering the system from the hot gas and then multiply it by 69%, you get 3%. So 3% of the Exergy destruction is inside the condenser. And this is the Exergy accounting of this Rankine cycle. So the output, so we have net power 30%. So 30% of the inputted Exergy is converted to the net power. And then we have couple losses here. Inside the condenser, we have 1% Exergy destruction. We have, this is an assumption, 1% Exergy destruction inside the stack. And then this is an assumption as well. We have the Exergy destruction due to the combustion. This is what we calculate, Exergy destruction inside the heat exchanger. This is the Exergy destruction inside the turbine. And then the Exergy destruction inside the pump is pretty small, I believe 0.03%. So we assume it is 0. And this is the Exergy destruction inside the condenser. If you summing up all of this, you will get 100%. So this is an example of Exergy accounting or Exergy analysis on a Rankine cycle. Okay, we have completed chapter 8 or chapter 2 of this thermodynamic 2. I suggest you to review it again, and then the next class will be talking about the problem example of this chapter 8 along with the quiz or polling. Thank you.